Okay, so our next topic is going to be how does pop really work? And this is big payoff in this one. So let's click on topic 2.2. And there we have it broken down into 4 different subtopics. So we're first going to do an overview of the whole periodic operating point analysis. Then we're going to zoom in on the core pop process, which is where all the really cool stuff happens. Then we're going to do 2 exercises where we look at all the ways that things can go wrong. And that will actually help you. We'll take the advantage of all the things we've learned about how it uses, and then learn how to, fix issues that we cause by the way we do things. So let's start out with topic 2.2.1. And this is an overview of the periodic operating point analysis. So let's start again by let's tidy up and don't save your schematic. Close the waveform viewer. All right, so the periodic operating point analysis, there's a number of, we're going to learn how to set it up. So there's certain parameters that control this process. We're going to talk about what those are and how to handle them. In order for POP to work, there has to be a trigger gate somewhere. So you have to tell POP how it knows that a new switching cycle has started. And the schematic POP trigger device is the easiest way to do that. So let's go to schematic 2.7. So we're going to go 2.7 AE, self-oscillating converter. Double click on that. Going to hit the home key, maybe blow it up. So you can do control scroll wheel to zoom in and out. Okay, so let's just run the simulation to start with. Okay, so we're doing the periodic operating point, and you can see that. So if we just look at what our analysis we picked, we said we're just going to do the POP analysis, and we're going to do, we'll go through all of this. Okay, so but it's just the POP analysis, no AC, no transient afterwards. Okay, so that's in fact what we have. And let's just take a quick look, because we're going to be looking at this a lot here. We have the POP trigger. So it went high here at t equals 0. And then, so every time we see a POP trigger transient, that's the beginning of a new cycle. And so we'll see how that gets set up. But here is the overview. Here's the basically, the big picture of what happens during a periodic operating point analysis. So there's 4 phases. We call them A, B, C, and D. Phase A is we load up the circuit with the initial conditions that you have defined. So we start with initial conditions that you present to the circuit. Then we're going to run n cycles, and you control n, of just a regular transient before we launch the core POP process. Okay, so we're going to start out with a given set of initial conditions. We're going to run n, an integer number of switching cycles before we launch the core POP process. Then the core POP process is going to do a number of simulations in the background where it's recursively adjusting all of the capacitor voltage and inductor currents in the circuit, in updating these initial conditions, running another switching cycle, updating the initial conditions, running another switching cycle. And basically, this is a software loop that operates around your hardware, your power supply circuit. And its sole task is it's trying to come up with initial conditions for all the energy storage elements such that this initial condition puts the simulation into a steady state condition. Okay, so that's the goal. It's trying to find a set of initial conditions that place the circuit into a steady state operation. Okay, once we've succeeded, then we run a specified number of cycles that you determine, and it's an integer number of cycles. That's really important, and that's what gets output to the waveform viewer. So in our case, we ask for 3 cycles. Okay, and this is this the steady state result. Yes.
So the n cycles that you specify for the output, then are they equivalent to the n cycles in step B?
No, so in the docs, we did a better job. I mean, and it's n cycle. This number of cycles and this number of cycles are independent of each other. You get to determine them.
Right, but
Okay.
you can specify the cycles in in step B too, because I haven't seen that one in the GUI.
Oh yes, oh yes, oh yes.
Right.
And we're going to go into that. We'll show exactly how to do that. Yeah. Okay. So there's a couple things. The pop process is assuming that the circuit is switching. So it's assuming that, it can look at the pop trigger and see that, there's switching action happening. So it looks at the output of the pop trigger and that's what it using to define when a new cycle starts. So the only way that Simplest knows that a new cycle starts is by looking at the output of this trigger device. Okay. If the circuit ever gets in a condition where it stops switching and the output stops switching, Simplest, the pop analysis will fail. It'll stop because, nothing's happening. So that's important to know. So the result of the pop analysis is we're trying to come up with a set of initial conditions for all the energy storage elements, as well as the switches and the logic that will put the circuit into a steady state. And the other thing is the closer your initial conditions are to steady state, the faster the core pop process is going to be able to converge, right? So, and you get to save yourselves time. So now let's go hit F8 or simulator choose analysis. You may notice that I never hit F8. I don't do it. So here is so we specified a pop analysis. Here is the pop tab that controls the analysis. And you can see that we've checked the box that says use this pop trigger device to do the analysis, okay? So where is this used? All right, so remember up here when we had our phases, we had phase A, B, C, and D. So what this little chart does is it says, where are we using the information that we give pop in this box, the pop trigger source definition? Well, it's used in all phases, all 4 phases of the pop analysis. Pop is counting on the pop trigger giving it critical information. Also, the next box, the trigger condition. So pop is looking at the output. Do you want it to trigger on the rising edge or the falling edge? That's a big deal. Okay. So you get to control that, and it does make a difference. So for example, you typically, when you want to find a place to put the pop trigger, you want to put it at a point where there's a very sharp edge. And so these are, there's opportunities for us to control all of that here. Okay. Also, there's some timing information that's very important. We have a parameter called the maximum period. So if you've ever done, programming for, say, like a microcontroller, particularly anything that has a user engaged with it, all right, you've run into the notion of a watchdog timer, right? Basically, if nothing happens in this amount of time, something's wrong. Something went wrong with the circuit, something's wrong, stop. Because remember, this whole the pop analysis is waiting for something to happen at the output. How long do you want it to wait before it decides, hey, there's a problem here, you need to go, take a look at it, okay? So that's That's what this maximum period is. This is the maximum amount of time you want simplest to wait for something to happen at the output. Because as we will see, there's lots of ways that you can, do something that makes it so that the output doesn't switch in the right amount of time, and you want it to stop so that you can fix it. Otherwise, you'd be sitting there waiting forever. This parameter is used again in all of these, every phase of the POP analysis. Then we have the cycles before launching POP. So that is phase B. So this, how many cycles, just regular transient runs, switching cycles do you want to do before POPs, you launch the core POP process, okay? And so that's this point. So what happens if you have this box checked and Simplest can't find the POP trigger? Well, you'll get an error message right away saying, you know what, this is a problem. This is a problem. And you said we should look for a POP trigger device. Can't find one on the schematic. You need to fix that. And so it actually gives you a really good error message. It said, you said use the POP trigger device, but there's no POP trigger device was found anywhere in your hierarchy. It doesn't just look on the top level schematic. It looks down into all the subcircuits. It looks everywhere. And it said, I looked everywhere I could, all the closets, the basement, everywhere, and I couldn't find it. So then it says, okay, what you need to do is place a POP trigger device, hook it up correctly. And here's where you go find it. You go to the view, and if you don't have the part selector already displayed, then go to view, show part selector, go to commonly used parts, and then pick out the POP trigger, okay? Again, we talked about the maximum period. This is the watchdog timer element, so you don't want this to be ridiculously long because that just wastes your time, right? You don't want it to be too short or else, that's a problem, but you want it to be a little bit longer than the longest that you would expect, a POP trigger to actually show
Tom,
up on your circuit. Yes, sir.
I'm still puzzled by the number of cycles you need to instruct the POP algorithm to start looking at a meaningful answer. How does it influence the precision or the type of response you get from Simplest? Why sometimes it works with 5 cycles, sometimes I need to push it to 100 or 120? Pushing the number of cycles, does it mean that something is wrong in the init file or something like this, for instance? Or
I can answer that, Tom.
Yeah.
Basically, the POP analysis, as Tom has explained, during the core POP process is like a software loop, and it can be very sensitive. So depending on your circuit and depending on the initial conditions, whether it is defined on the schematic or defined in the init file, if they are far away from your steady state, then if we run the core POP process right away, and depending on the complexity of the circuit, especially those circuits that has protection, saturation of op-amp and whatnot, the core POP process can then drive the simulation to a unreasonable place because you see some, for instance, current limiting or shutdown and whatnot. So the number of cycles before launching POP is just basically a simple transient analysis being carried out before the core POP process is initiated. So if you have a simple circuit, and for instance, if it's a buck converter, which is relatively benign, then you just need a small number here. On the other hand, if the circuit is more complex or the given initial condition is very far away from the steady state, or it is close to a different steady state than you have envisioned, then you may need to increase that number of cycles before launching POP.
Yeah, that's a very good point. So 3 is actually a very small number, and you'll see why. When after the break, you'll see why we picked 3. First of all, we use this in the training class all the time. We know the circuit. We know how to initialize it, so it can converge nicely with 3. Also, the dynamic range of this circuit is very narrow. It just doesn't work very well. This circuit was very popular when cheap trumped everything. So being a cheap circuit was better than being an efficient circuit. And so it doesn't, it's not a stellar performer, but it's a great example of all the things that we need to talk about in the training course. What I would suggest is a reasonable number. A good number is 20. It's pretty rare. So what this does is we're going to run 20 transients just to get the circuit so everything is doing what it's supposed to do. It's not often some, crazy state. All the logic is kind of woken up and it's doing its thing. And depending, like Ron said, on the complexity, you may need more than just a few cycles. You likely will need a few cycles. So you want it to be going in the right direction before we launch the core pop process.
Right.
This
So
is
if you would
usually
have,
a good number.
okay, if you would have a 20 millisecond soft start sequence first, for instance, so you would like to squeeze it to the smallest you can before starting the pop in that case?
Well, so in general, you don't want to use pop to power through a soft start. We have our PFC example has a real nice, you want to initialize the soft start to be where it's supposed to be in steady state. There's no benefit in forcing the circuit to run to go through a soft start.
There are some circuits that are, especially controllers, that really require soft start to work. Is almost impossible to know the initial condition beforehand, and because they test the input voltage, test some all kinds of conditions. So in that case, that's why Christoph, we are talking about that pre-pop transient that would be coming in the future for your soft start first.
Yeah. What I'm saying is, it doesn't necessarily apply to some of the really complex controllers that are coming out today that are solving, really challenging problems. Yeah. So that what Ron said and what you were suggesting is correct. If you have to go through a soft start, then you'll just have to figure out what this number needs to be. It's ideally, there's a way of initializing the circuit so you can avoid having to do a soft start. That's the goal. That's the goal.
Okay. And what I was doing is I was running a cold start transient analysis, for instance, and then was measuring the time at which the out reaches target, and then I, let's say, divide more or less the amount of time by the switching cycle to have an idea of what the pop cycle should be.
Correct.
Okay.
So if you have to do that, then that's the way to go.
Okay.
But yep. But in general, go ahead. Sorry.
Yeah, there's also some converters that go into hysteretic mode during startup or at light load conditions where you might want to have that long delay time, the longer delay, the longer period before you launch pop.
Yep. Sometimes people use this as this is kind of like the desperation move. I've seen some where people had 2,000 cycles because they couldn't get pop to converge, and this was their desperation move.
There's also it wasn't intended this way, but since the maximum limit is high, for some simple converters, I've seen users to use this cycle before launching pop as a way to include a soft start in their simulations.
Yep.
Unfortunately, you don't have this initial condition then saved. So I guess the easier way is maybe running the long transient, saving the initial conditions, and then go with a short cycle count in.
Yes, exactly. That's what I'm saying. You want to know where your .init file is saved so that you can run. Because initially, you do need to watch your circuit go from 0, 0 all the way up, and it's doing what it's supposed to do. But if you can, if it's possible to initialize the circuit in steady state, then grab that .NET file that is after the long transient, use that to initialize your circuit to do a pop analysis, and then save that so that now you can just put the circuit into steady state right off the bat. That's a very, very good way to do this. Okay, so I think we've talked about the overview. So now we know, basically we start off with a set of initial conditions. We run this many cycles before launching POP, the core POP process. The core POP process runs, and then we launch a different number of switching cycles, which, by the way, is this number right here, Jens. We'll get to that after the break. But this is where you control how many cycles run after POP. And so we're going to take a break now.